Section: Contents. In this section, we will discuss our vision for large language models and how we aim to empower the community with enhanced intelligence through the YE model series. Our models, the 6B and 34B language models, have been pre-trained from scratch on a vast amount of carefully curated data and fine-tuned to achieve impressive benchmark scores and human-like preferences. When designing the YE model series, we focused on key aspects such as model scale, and data quality. We chose the 34B model size to strike a balance between performance and cost, ensuring it can run efficiently on standard hardware. To compensate for the smaller model size compared to other models, we increased the amount of pre-training data to 3.1 T tokens, optimizing the model data scale combination for better performance. Our approach to data engineering prioritizes quality over quantity, with rigorous cleaning processes for both pre-training and fine-tuning data. By handcrafting instructions based on user feedback and employing advanced filtering techniques, we ensure high data quality, which is crucial for the success of our models. In terms of model architecture, we utilize a standard transformer architecture with specific modifications to enhance performance. Our fine-tuning dataset is carefully curated from multi-turn instruction response pairs, refined through user feedback iterations to improve model accuracy. We have expanded the capabilities of the YE model series in 3 dimensions: context scaling, vision language adaptation, and depth upscaling. By continuously pre-training the model on extended data, integrating a vision encoder, and increasing model depth, we have enhanced its performance across various tasks. Our infrastructure supports the full development cycle of the YE models, from pre-training to fine-tuning to deployment. Through efficient task scheduling, resource allocation, and quantization techniques, we have achieved performance on par with GPT 3.5 while ensuring cost-effective deployment on consumer-grade devices. Overall, the YE model series offers high-quality, cost-effective models for researchers and developers, enables user privacy through locally deployable chatbots, and sets a path for future advancements in data and model scaling for both research and commercial applications. Section Summary. In this section, we introduce the YE model series as a step towards our vision of large language models becoming the next-generation computational platform. We focus on model scale, and data quality, achieving near GPT 3.5 benchmark scores and human preferences through substantial engineering efforts. Our YE 34B model matches GPT 3.5 in performance and efficiency, providing cost-effective models for researchers, locally runnable chatbots for end users, and guiding future data and model scaling for stronger frontier models in research and commercial applications. Section: Pre-training. In this section, we describe our approach to pre-training. We trained a standard dense transformer architecture on a large pre-training dataset with the belief that extensive high-quality data can enhance the model's capabilities without requiring significant architectural modifications. Although we conducted various architectural experiments, our focus was on leveraging the power of the data. We first elaborate on our data processing pipeline, which involves carefully designing a series of data cleaning strategies to ensure quality and diversity in our bilingual pre-training data. This includes filtering out low-quality text based on various criteria and anonymizing personal information like email addresses and phone numbers. To address more complex cases beyond simple rules, we incorporated learned filters. These filters, such as the perplexity score and safety score, help identify and eliminate inappropriate content like pornography and violence. Additionally, we utilized cluster-based filters for semantic grouping of web documents and deduplication techniques to remove redundant content. For tokenization, we employed byte pair encoding, BPE, to tokenize the data, ensuring computational efficiency and word comprehension. Our model architecture is based on a modified decoder-only transformer design, with specific attention mechanisms like grouped query attention, GQA, to optimize training and inference costs. Overall, our pre-training process involved meticulous data processing, advanced filtering techniques, and efficient tokenization methods to prepare a high-quality dataset for training our transformer model. Section Summary. In this section, we pre-train a standard dense transformer architecture on a carefully curated large corpus, assuming that extensive high-quality data can enhance the model's capabilities without requiring significant architectural modifications. Our data processing pipeline involves heuristic rule filters, learned filters, cluster-based filters, and deduplication techniques to ensure the quality and diversity of the bilingual pre-training data. Additionally, we tokenize the pre-training data using byte pair encoding with a vocabulary size of 64,000, and implement a modified version of the classical decoder-only transformer architecture with grouped query attention, GQA, to optimize training and inference costs. Section. Activation function. In this section, we utilized SWI-glue as our post-attention layer, adjusting its activation size from 4 times the hidden size to 8/3 times the hidden size to match the standard post-attention layer. This adjustment helps maintain a similar parameter count as existing 7B and 34B models. For positional embedding and handling long context, we employed rotary position embedding, ROPE, with a modified base frequency, ROPE ABF, to support longer context windows up to 200K tokens. By pre-training the model on 10B tokens with extended sequences, mainly from books, we observed that the model can effectively handle context lengths ranging from 4K to 200K with just 1 to 2B tokens. This suggests that the model inherently possesses the ability to model dependencies longer than its pre-trained length of 4K, and fine-tuning further enhances its performance in handling long contexts. Our fine-tuning approach prioritizes data quality over quantity, contrasting with data-intensive methods that scale to millions of entries without thorough examination. By focusing on a smaller dataset of less than 10K carefully constructed instruction-response dialog pairs, we ensure that each data point is optimized. This meticulous approach has shown superior results compared to larger but less curated datasets. To enhance prompt distribution selection, response formatting, and chain-of-thought formatting, we implemented various techniques such as developing compound instructions, structuring responses in an introduction body conclusion format, and using a step-back pattern to reduce hallucinations and repetitions in the responses. To ensure diversity in capabilities, we included a wide range of open-source prompts covering different areas like question answering, creative writing, reasoning, mathematics, coding, and bilingual capabilities. By implementing an instruction tagging system and a diversity-focused sampling algorithm, we balance the distribution of instructions across various tags to create a diverse fine-tuning dataset for improved cross-task robustness. Additionally, we experimented with different proportions for each capability using an approximate grid search process guided by validation results and human evaluation sets to determine the optimal data mixture. We also introduced the ChatML style format to structure the data effectively, enabling the model to distinguish between system configurations, user inputs, and assistant responses. Section Summary. In this section, we adjust the activation function size in our post-attention layer to maintain parameter consistency with existing models. We also enhance our model's ability to handle long context by utilizing rotary position embedding and focusing on data quality over quantity during fine-tuning, resulting in superior performance with a smaller, carefully curated dataset. Additionally, we ensure diversity in our fine-tuning dataset by including a wide range of prompts and developing an instruction tagging system to balance different capabilities, ultimately improving cross-task robustness. Section. Training method. In this section, we utilize a next word prediction loss for fine-tuning our model. We focus on computing loss only on the responses, excluding system and user instructions. We employ the Atom W optimizer with specific settings for beta values and epsilon. Our setup includes a sequence length of 4096 and a batch size of 64. The training process consists of 300 steps with a fixed learning rate, weight decay, gradient clipping, and NEF-tune with noise scale parameters for different models. Regarding infrastructure, we have developed a system that supports various tasks such as data processing, pre-training, fine-tuning, and serving. Our infrastructure features automated management and monitoring of computing resources, enhanced training speed through optimized strategies, a unified fine-tuning framework for distributed training, and cost reduction techniques for deployment. To efficiently handle large-scale language model development, we have implemented a multi-cloud task scheduling algorithm and a high-performance training framework. We address reliability challenges by automating error detection and recovery processes. Additionally, we have a user-friendly interface for managing training tasks and parameters. Memory and communication constraints are major challenges in large-scale model training. We employ techniques like 0-1, tensor parallelism, pipeline parallelism, kernel fusion, and topology-aware resource allocation to overcome these challenges effectively. In fine-tuning frameworks, we orchestrate multiple models using a scheduling framework to support various backends. This approach improves training speed and resource utilization significantly. For fast and efficient inference, we utilize quantization, dynamic batching, and page detention techniques to enhance decoding speed and memory efficiency. We also implement strategies to support long context windows up to 200K without modifying the model architecture. Section Summary. In this section, we utilize a next word prediction loss for fine-tuning, focusing only on responses and not system or user instructions. Our training method involves using the Atom W optimizer with specific parameters, a sequence length of 4096, and a batch size of 64, along with various techniques like Neftune for different chat models. Additionally, we detail our infrastructure setup, including computing resource management strategies for large-scale language model development, performance and cost efficiency improvements, a fine-tuning framework supporting multiple models, and techniques for fast and efficient inference, all aimed at enhancing long context window support up to 200K for pre-training and fine-tuning without modifying the model architecture. Section: Safety. In this section, we developed a full-stack responsible AI safety engine, RAISE, to ensure the trustworthiness and safety of our model. RAISE focuses on safe pre-training, alignment, and deployment. We implemented safety measures during the pre-training and alignment stages. In pre-training, we used filters based on heuristic rules, keyword matching, and learned classifiers to remove text containing personal identifiers, private data, and inappropriate content like sexual, violent, and extremist material. During alignment, we created a comprehensive safety taxonomy covering various concerns such as environmental disharmony, discriminatory practices, hate speech, and cybersecurity threats. We curated datasets reflecting these categories to align our model effectively. Additionally, we included prompts simulating attack scenarios to enhance the model's resilience against misuse. Our evaluations show that the Yi model family performs well across different tasks and is comparable to GPT 3.5 in terms of user preference. We present results for our base models and compare them with other established models on standard benchmarks. We observed differences in results between our pipeline and public sources when benchmarking open-source models. These variations are mainly due to different prompts, post-processing strategies, and sampling techniques used by various models. Our prompt and post-processing strategy align with the default settings of the original benchmarks. By training on a larger number of tokens, we achieved significant performance improvements across various benchmarks. However, there are still noticeable gaps between our model and existing models, especially in tasks related to mathematics and coding. We plan to enhance our model's capabilities in these areas in the future. We found that larger model sizes, like Yi 34B, lead to better performance on tasks related to code and math compared to smaller models. Models with higher quality pre-training data tend to outperform larger models with lower quality data. Open-source language models still fall behind GPT-4 and GPT 3.5 in terms of performance on different benchmarks. Bilingual models like Qwen 14b and Yi 34b show promise in matching or surpassing GPT-4 on Chinese knowledge-related tasks but struggle to compete on reasoning-related benchmarks like code and math. Section Summary. In this section, we develop a responsible AI safety engine, RAISE, to ensure the trustworthiness and safety of our model through safe pre-training, alignment, and deployment stages. We implement safety measures in the pre-training and alignment phases by filtering out sensitive content and curating datasets to cover a wide range of potential concerns, ultimately enhancing the model's resilience against malicious use. Our evaluations show that our YE model family performs well across various tasks, approaching the user preference rate of GPT 3.5, with notable performance gains in mathematics and coding benchmarks due to our substantial training data size. Section: In-Context Learning Study. In this section, we delve into the study of in-context learning. We aim to understand how well a model can figure out the linear coefficients of a weighted sum based on a few input-output examples. The task involves inferring the values of W_1, W_2, W_n in the equation y equals W_1x_1 plus W_2x_2 plus W_nx_n given input values x_1, x_2, x_n and the corresponding output y. We evaluate the model's performance by measuring the difference between the predicted output y and the actual output y * as a continuous measure, and by checking if the predicted output exactly matches the actual output as a discontinuous measure. Most models perform well on basic arithmetic operations like addition and subtraction, so we can rule out arithmetic skills as a factor influencing performance. When we set the linear coefficients to be 1, -1, we find that YE34B and Llama 270B perform the best in terms of exact output matching. However, when we increase the number of linear coefficients to be 1, 1, 1, 1, 1, we observe that only larger models like Llama 270B and Mixtral can achieve high scores on exact output matching, even though the differences from the target output are more continuous. These findings suggest that YE34B excels in context learning, and scaling up may enable the model to handle more complex functions through this learning approach. Moving on to the evaluation of our chat model's performance, we first focus on automatic evaluations. We use greedy decoding to generate responses and assess accuracy by comparing the model's answers with the correct ones. To ensure fair evaluations, we use consistent prompts for all models when evaluating their responses to the same set of questions. Our evaluations involve generating responses based on explicit or implicit instructions, such as those provided in few-shot examples. We extract relevant answers from the generated text and employ the chain of thought (COT) approach for shot evaluations on the GSM-8K and BBH datasets to guide the model in reaching accurate answers. The results demonstrate the effectiveness of our chat models in understanding human instructions and generating appropriate responses. Notably, the 4-bit quantization significantly reduces memory requirements without substantially affecting model performance, making it feasible to deploy the model on consumer-grade devices. We emphasize that our evaluations aim to ensure that our model's foundational knowledge and capabilities are maintained, rather than optimizing performance on benchmarks. Additionally, we assess the model's proficiency in mathematical computations by subjecting it to the 2023 Hungarian High School Mathematics Final Exam questions, revealing varying capabilities among different model sizes. In the realm of human evaluations, we assess the conversational abilities of our model to ensure its efficacy and safety. We utilize a range of evaluation datasets from the community and construct our own dataset to comprehensively evaluate the model's conversational skills. However, evaluation results can be influenced by assessment criteria and prompt designs, potentially leading to biased outcomes. Therefore, we present external evaluation results to showcase our model's conversational abilities objectively. These results include assessments from Alpaca Eval, LMSY's Chatbot Arena, and SuperCLUE, highlighting our model's bilingual dialogue capabilities and alignment with user preferences. The data indicates that our model performs well in English and Chinese conversations, although there is room for improvement compared to GPT-4. Additional comparative results are available for review on the official website, demonstrating performance enhancements as the dataset scales up. Section Summary. In this section, we investigate the in-context learning capability by inferring linear coefficients from few-shot input-output demonstrations. We use measures like absolute difference and exact match to evaluate model performance, observing that larger models excel in inferring more complex functions. Additionally, we assess the conversational abilities of our chat model through automatic and human evaluations, showcasing proficiency in understanding human instructions and generating appropriate responses, particularly excelling in bilingual dialogue capabilities. Section: Capability Extension. In this section, we will discuss our methods after training to enhance the Yi base model to handle longer contexts of 200K, give it visual understanding abilities, and improve the 6B model by increasing its depth. For handling long contexts, we have a two-phase solution: continual pre-training and fine-tuning, both of which are lightweight. We believe that the base model already has the potential to use information from anywhere within the 200K input context. The continual pre-training phase helps unlock this capability, as shown by its strong performance on the needle in a haystack test. The fine-tuning phase then adjusts the model's responses to better match human instructions and preferences. During the continual pre-training, we use full attention models with sequence parallelism and distributed attention, avoiding sparse or linear attention mechanisms. We pre-train the Yi 6B, 34B base model on a mix of original pre-training data, length upsampled long context data from books, and synthetic multi-document question answering data. This approach aligns with common data engineering practices. The model is pre-trained on 5 billion tokens with a batch size of 4 million, equivalent to 100 optimization steps. In supervised fine-tuning, we combine short context data with long context document question answering data. We use automated methods to create document question answering pairs, encouraging the model to retrieve information from the input rather than generating answers internally. The fine-tuned model is available for use, and its performance is detailed in figures and tables. Moving on to vision-language integration, we introduce Yi Vision Language, Yi VL, models, Yi VL6B and Yi VL34B, based on Yi 6B chat and Yi 34B chat language models. These models incorporate image understanding capabilities using a vision transformer, VIT, for image encoding, a projection module to align image and text features, and a large language model for understanding and generating text in English and Chinese. The Yi VL models undergo a three-stage training process involving training the VIT and projection module, scaling up image resolution, and training the entire model for multimodal chat interactions. The training datasets include millions of image-text pairs from various sources to enhance the model's proficiency in understanding both visual and linguistic inputs. The training parameters and settings are adjusted across the stages to optimize model performance. The training process for Yi VL models utilizes multiple GPUs and takes several days to complete. The model's performance is evaluated on the MMMU testset leaderboard. As research in this area progresses, we aim to continuously enhance and update the performance of Yi VL models. Section Summary. In this section, we discuss our methods to extend the Yi base model to 200K long context, add visual understanding capability, and enhance the 6B model through depth upscaling. Our approach involves continual pre-training and fine-tuning phases to unlock the model's potential in utilizing information within the 200K input context, leading to strong performance on tasks like the needle in a haystack test. Additionally, we introduce Yi Vision Language, Yi VL, models that integrate image understanding capabilities into large language models, showcasing proficiency in understanding and generating both English and Chinese through a three-stage training process. Section: Depth Upscaling. In this section, we explore depth upscaling. We have observed that improving model performance is predictable when we increase the computational budget, model size, and data size. However, determining the best way to distribute resources between model and data sizes as we expand the computational budget remains a significant challenge in scaling laws. Research has shown that allocating more computational budget to scaling the model should be proportional to the quality of the available data. Based on these findings, we introduce a new approach to adjust the allocation of resources between data and model sizes dynamically through a series of training stages. This method fine-tunes the balance between data characteristics and model size iteratively, following scaling laws, to enhance both model training efficiency and performance. To implement this approach, we aim to scale up our Yi6B base model with 32 layers to a Yi9B model with 48 layers by duplicating the original 16 middle layers, 12 to 28. This process involves increasing the depth of the base model and continuing the pre-training phase for the upgraded model. Our investigations suggest that deciding which layers to replicate can be guided by evaluating the similarity between the inputs and outputs of each layer. By assessing the cosine similarity scores, we can target specific layers for scaling without requiring additional pre-training, resulting in minimal performance impacts. This minimal impact is due to the high cosine similarity between the inputs and outputs of the duplicated layers, indicating that replicating these layers does not significantly change the output results of the original model. This method ensures efficient model scaling by optimizing its architecture based on the internal processing dynamics of its layers. In terms of continual training, our dataset consists of around 800 billion tokens across 2 stages, with 70% of the data recently collected and carefully selected. We have improved code coverage in the final stage to enhance performance. To optimize the training process, we maintain a constant learning rate and gradually increase the batch size whenever the model's loss plateaus. This incremental adjustment, along with keeping other parameters aligned with the Yi6B base model configuration, has been crucial for successful training at scale. The effectiveness of these strategies is demonstrated in the performance of the Yi9B base model across various benchmarks, showcasing its competitive advantages in specific domains and highlighting the success of our methodology in enhancing model performance by adjusting the interplay between data characteristics and model size optimally. In our final discussions, we present the development of the Yi language model family, with the Yi34B model achieving performance comparable to GPT 3.5 and being deployable on consumer-grade devices. We emphasize the importance of data quantity and quality in the pre-training process, recommending training models on larger datasets for consistent performance gains. We also stress the significance of data quality, particularly the source of the data and the details of data cleaning. Additionally, we discuss the fine-tuning procedure, emphasizing the iterative process on a small amount of data and the importance of real user feedback for improvement. Our approach differs from traditional scaling methods and focuses on optimizing data to scale up model parameters for stronger models in future versions.